Next topic is about your convection. Okay. So what do you mean by convection, beta? Like say you heat the water on your stove. So water from the higher potential, it will try to go for your lower. So there is a rotation of the liquid from one point to the another point. That means actual movement of the molecules is taking place in the convection, I can say. So I can say that it is the phenomenon of heat transfer. It is the phenomenon of heat transfer by actual movement of particles. By actual movement of your particles. Okay. So generally it takes place in your liquids and gases. We don't see the convection in your solids, but in solids it is absent. In solids it is absent. Is it clear for everyone? The phenomenon of the heat transfer by the actual movement of the particles from one point to another point, like example liquids and gases. And the convection is not seen in your solids part of a lesion. Okay. Example I can write here. The fluid heated in a container. Okay, a fluid heated in a container. So when you heat the water in a stove, or for the what do you call that, when you keep a heater in the water and start heating it, so what happened? The lower part of the liquid will get heated up, so that will go up again. On colder part of the liquid will go down, and there will be the circulation of your liquids like that. So I can say that this rate of your heat convection, the rate of heat convection from an object is such that heat transfer is right now happening. So it is dq by your dt, dq by your dut due to your convection. Q is the energy, T is your time, is equals to R is directly proportional to area and also directly proportional to the temperature difference. So removing this one, I can write here dq by your dt due to your convection is equals to some constant known as of your H into A into your delta theta. A is nothing but area, delta theta is your temperature difference, and H is nothing but of your constant. This H is known as of your convection constant. Convection constant or coefficient, we can say, or coefficient. Delta T is the temperature difference of object and the fluid. This one is your temperature difference between object and fluid, convection fluid, whatever you're taking. And A is nothing but of your contact area. A is nothing but your contact area. This is only the formula in the convection you need to remember. dq by dt is equals to your H into A into delta theta. A is your convection constant or coefficient. A is your capital A is your area of contact. H is your convection constant or coefficient. And delta T is your temperature difference between the object and as well as of your fluid part of relation. Clear for everyone, beta? Is it clear? Sure. Next one is about your radiation. What is the radiation I told you, beta? Medium is not required. Medium is not required for the propagation of your light or heat energy, I can say. Okay, so this is an electromagnetic wave part of relation. So the phenomenon of the transfer of the heat necessary from one point to another point in the form of electromagnetic wave is called of that one. So rate of emission of this body will depend on, radiation will depend on, this is also very important for theory question, beta, depends on number one, nature of surface of your body. Okay, and number two, it is also depending upon your surface area of the body. Surface area of the body, very important, what type of surface the radiation has been falling. And third one is temperature of your body and surrounding. temperature of the body, and what is the surrounding to it. So it depends upon how the heat energy has been taking place. So radiation depends upon the nature of the surface of your body. It also depends upon the surface area of your body, and it also depends upon the temperature of the body and as well as of your surrounding part of relation. Clear? So if I'm talking about some basic properties, beta, these are completely invisible. Electromagnetic lines, it lies in infrared region. Infrared region. Wavelength range is from wavelength range is from 4 into 10 to the power of minus 4 meters to approximately 7.5 into 10 to the power of minus 7 meters. This is important point, beta. Electromagnetic radiations lies in which region means this radiations is lying in your infrared radiations, in the infrared radiations, and wavelength ranges from your 4 into 10 to the power of minus 4 meters to 7.5 into 10 to the power of minus 7 meters per deflection, and it travels with the speed of your light. Travels with the speed of your light. That is how much? 3 into 10 to the power of your 8 meter per second. Almost all that part deflection. Okay. So it exhibits the phenomenon. Electromagnetic radiation exhibits the phenomenon. I can say it exhibits the phenomenon of reflection. It undergoes the reflection. It undergoes your refraction. It also undergoes your interference. It also undergoes your diffraction and polarization. Something like of your wave optics. Okay. So radiations exhibits the phenomenon of your reflection, refraction, interference, and transmission also bit. And transmission also. It also transmits from one body to your another body. If it is an opaque body, it will stop. If it is a transparent body, it can transfer from one body to your another body. So radiation exhibits a phenomenon of your reflection, refraction, interference, diffraction, polarization, and your transmission of your light from one point to the another point per deflection. Clear? Sure. The next one. It obeys inverse square law. It obeys an inverse square law. What is that? Like intensity is inversely proportional to the square of the distance between them. I is your intensity of radiation and D is your distance from the source beta. Okay. So it can be taken. So intensity is inversely proportional to your square of density. What is actual intensity beta? Intensity is nothing but what? Power divided by area. But the point to source, if I'm taking, so it is a power divided by area is 4 pi into your R square. The power of the source is a constant, 4 pi is a constant, so intensity will be inversely proportional to the square of the distance. Very, very important. But a lot of theory questions have been based on this topic beta. 1 or 2 are formulas there on Stefan's laws and Newton's laws of cooling are only the relations on which we have the problems related to this topic basically. Okay. The next one and very important theorem called as of your reversed theory of your heat exchange. Reversed theory of your heat exchange. Now see, if you want to measure the radiations better, you can measure the radiations by a bolometer, isn't it? You can measure the radiations either by your bolometer or you can also use your thermopiles. Or also you can use your thermocouple, combination of 2 different metals. Also you can use your pyrometers, very high temperatures, radio micrometers, they are also being used, and some thermal scopes also being used right now. Thermal scopes. Okay, something like that. So in order to measure the temperatures, we generally use your bolometers. Like say if you might have been seen the Ironman 4 or Ironman 3, there is a situation where I can tell you later, bolometer is an instrument by which we can measure the heat sensations better. Different bodies, even though if they are a larger distance, we can measure their temperatures. That is called as of your bolometers. So previous theory of your heat exchange. What does this says is right now see here. All right, this given condition. Every body, sorry. Yeah. Every body emits and absorbs heat radiations at all temperatures except at absolute zero, except at your absolute zero. What is that? Minus 273 degrees centigrade. So everybody observes and everybody emits and absorbs the heat radiations at all temperatures except at your absolute zero is the theory given by the previous theory, which is called as of your previous theory of your heat exchange part of relation. Clear, beta? It depends upon the temperature and it is independent of your surrounding, beta. So it depends on, I can say, depends on temperature of body and independent of surrounding temperatures and independent of your surrounding temperature. Okay, it is independent of your surrounding temperature. That means if a body emits more heat energy, beta, then what absorbs from the surrounding, then it will be the temperature fall. If the body absorbs more heat from the surrounding, then what it emits, then it will be the temperature rise. That means if the body is emitting and absorbing the heat in equal amount, then it is said to be in thermal equilibrium. Clear? When the temperature of the body and the surrounding are equalized, then convection stop and only radiation exchange will be taking place part of relation. Clear for everyone? Isn't it? So in the previous theory of your heat exchange part of relation, what exactly is happening is whenever heat is being observed, maybe the temperature of that body might be increasing or decreasing depending upon the temperature by what it is been observing right now, isn't it? So sometimes what happens if your body emits more heat, isn't it, than what it absorbs, isn't it, from the surrounding, then what happened to its temperature? Obviously its temperature will fall. If your body absorbs more heat energy from the surrounding, then what it emits than what it emits, then what happened to the temperature? The temperature will rise. See, when a body is emitting more amount of your heat energy rather than it is taking very less amount of energy, so in that condition the temperature will be falling down. Now say for example, if the body is absorbing more heat energy and it is emitting very less amount of energy, then what is happening to the temperature of that body? The temperature of the body will rise. The temperature of the body will be rising. That was the theory given by your previous teacher. That means if you are absorbing a lot and giving very small amount, then the temperature of the body will be rising. If you are emitting a lot and you are observing very small, then the temperature of the body will be falling down. That was the statement given by your previous theory. Is that clear for everyone? Sure. The theory only, but only we get a numericals based upon that one. Very less, only theoretical questions you need to remember. The next side heading is for this one, perfect Blackboard. Perfect Blackboard. What exactly is a perfect Blackboard? Anyone better? Body which absorbs all heat radiation incident on it is called as of your perfect black body. So I can say that it is a body which absorbs all heat radiations incident on it. Okay, that is called as of your perfect black body. Okay, so what is happening is on heating, it emits radiations of all possible wavelengths at a given temperature. So I can write here on heating, it emits radiations of all possible wavelengths at a given temperature. That means if this is a body, this is emitting the red, it is emitting your yellow, if it is emitting your violet, it is emitting your green, if it is emitting your what do you call that one, orange, it is emitting your blue. So if all the radiations have been emitted with all the possible wavelengths, then such type of your bodies are called as of your perfect black body. It is called as your perfect black body. So on heating, it emits the radiations of all the possible wavelengths at a given temperature is called as your perfect black body. And the wavelength emitted by this radiation depends on the temperature, beta. Depends only on the temperature, but are independent of material. Okay, so it depends only on the temperature and it is independent of your temperature. Sorry, independent of your body. Like example, if I'm taking your lamp black, okay, and this is absorbing 96% of your heat radiations. If I'm taking your platinum black, this is almost all 98%, isn't it? And wings body, wings black bodies are artificial, are your artificial black bodies. Okay, and what is our natural black body, beta? Can anyone tell me? What is our natural black body? Anyone? Sun. Sun is our natural black body. Black holes. Sun. Sun is our natural black body. Okay. So what is an artificial black body means? Paris black body you can write. You can write even one more word. Paris and wings black bodies are your artificial black bodies. Lamp black is a perfect black body, almost 96%, and platinum black. See, whatever the heat absorbing it has been, it is not depending upon the nature of material beta. It is independent of material. Depends on what beta? Temperature. Depends on temperature. These are all theory questions, but compulsory you need to remember, otherwise you may be losing the marks. So for perfect black body, it is a body which absorbs all the heat radiations incident on it. On heating, it emits the radiations of all possible wavelengths at the given temperature. Some of the examples of the perfect black body are lamp black, platinum black, Paris and wings black bodies are artificial black bodies. Sun is our natural black body, and it is independent of your material and depends upon your temperature part of relation. Clear, beta? Sure. Next Saturday, emissive power. Emissive power. Represented by letter capital E. Emissive power. See, it is nothing but energy emitted per unit area per unit time beta. So it is the amount of energy it is amount of energy radiated by unit surface area per second at a given temperature. In a given wavelength range. Okay, so it is the amount of energy radiated by what beta? Unit surface area, by your unit surface area per second at a given temperature in a given wavelength range. So I can write this formula as E is equals to energy divided by area into your time. So this is your formula. E is equals to your energy divided by your area into time. Can anyone tell me the unit of this one beta? Energy divided by time is measured in your watt power, divided by area is measured in meter square, watt per meter square. Okay, so this depends on emissive power, depends on nature of surface bit, nature of your surface and also the temperature. Whereas perfect black body is independent of nature of material and depends only on temperature, whereas emissive power of a body will depend upon the nature of the surface and as well as of your temperature. Okay. Sure. Next one is absorptive power. Absorptive power, represented by letter A. So the word itself is very clearly indicating, isn't it? So amount of energy absorbed per your unit. That means for a given wavelength and temperature beta, it is the ratio of the radiant energy absorbed by unit surface area per second to that of your incident on it. That means I can write here A is equals to amount of energy absorbed divided by amount of energy incident on that one. As both of them are same, so it has no units because both of them will get cancelled. So absorptive power is nothing but the ratio of your energy absorbed per your unit area per unit time divided by your unit area amount of energy incident per your unit area per unit time. So for perfect black body, I can write for perfect black body, for your perfect black body, absorptive power is equals to 1 because energy incident will be equal to energy absorbed. Okay, so I can say that absorptive power will depend on, it depends on nature of surface, it depends on your nature of surface and the temperature of body and your temperature of your body. Very important formula, but very important formula. Absorptive power is nothing but of your amount of energy absorbed per your unit area per unit time divided by amount of energy absorbed incident per unit area per unit time. As both of them are energies, it has no units. For perfect black body, A value is taken as of your 1 because an absorptive energy will be equal to your reflective energy. Whatever it has been incident, the same amount of energy will be your absorbed on this body. Okay. The next one and very important term in this one is emissive power. Emissivity. Next one is your emissivity. Emissivity, or we can also call as of your relative emittance. Relative emittance. Emissivity, or also known as of your relative emittance, represented by letter small e. Represented by letter small e. So what is this small e beta? See here, E is nothing but, see, emissivity or relative emittance, that means the power to give it, isn't it? That means emissive power, see the formula. This one is your emissive power of a body. Emissive power of your body. That means what extent it can emissive. That means give divided by emissive power of a perfect black body. Of a perfect black body is called as of your emissivity. Okay, so ratio of emissive power of a body divided by emissive power of your perfect black body is called as of your emittance. That means it is E divided by emissive power of your black body, or else energy at a given wavelength divided by energy of a given wavelength into some constant B. Okay, so for perfect black body, for perfect black body, emissivity is taken as of your 1. For any other body, if I am taking, for any other body except black body, for any other values, if I am taking, the value of this one will be 0 lesser than E and E lesser than of your 1. Clear, beta? Sure. So what is an emissivity? Emissivity is also known as relative emittance, represented by letter E. E value is 1 for your perfect black body, and for all other bodies, it is in between 0 to your 1 particulation. It is the ratio of the emissive power of your body divided by emissive power of your perfect black body. Just go through it better once faster. Sure. Done, beta. Next. Kirchhoff's law. Before that, let me write one small point here. For any body beta, ratio of your absorptive power plus reflective plus transmission is always equals to 1. T is your transmittance, R is your reflecting power, and A is your absorpting power. For perfectly black body, or I can say for your black body, reflectance is 0, absorptance is equals to your 1, and transmission will be equal to 0. There is no reflection and there is no transmission, so absorption will be equal to 1 for your black body. Very important point. Okay, for any body, absorptive power plus reflective power plus transmittance must be equal to your 1. For a perfectly black body or for a black body, reflectance power is 0, transmittance power is 0, so absorptive power will be equal to your 1. Now see, Kirchhoff law beta. Kirchhoff frame. Laptop is little bit larger. Okay. So do anyone remember the Kirchhoff law beta? What exactly is of your Kirchhoff law? What exactly is the Kirchhoff law beta? Do anyone? Nandini, what is the Kirchhoff law? See here, for a given temperature and wavelength, very important beta. For a given temperature and wavelength, the ratio of emissive power, that means to what extent it is emitting, the ratio of emissive power to your absorptive power is constant. That means E at a particular wavelength divided by absorptive for a given wavelength will always be your constant. The ratio of your emissive power divided by your absorptive power will always be equal to your constant. That means good emitters are your good absorbers part of relation. That is some constant I am taking right now. So I can say that energy at a given wavelength will be directly proportional to the absorption of your given wavelength. Okay. That means good absorbers are your good emitters, I can say. So I can say that good emitters are good absorbers. Okay, and vice versa also. And vice versa. Okay. So E at a given wavelength, whatever it is emitting, if it is directly proportional to your absorptive. So if I'm giving some, say for example, X amount of a ray for a given body, if it is absorbing the complete X amount of a ray, then such type of your bodies are said to be undergoing your good emitters and as well as of your good absorbers. So the ratio of your E lambda by your A lambda, if it is constant, that constant I'm representing it by letters, say for example, some V. So the ratio of emissive power to the absorptive power is a constant for a given temperature and as well as of your wavelength. So E lambda by A lambda is equals to your constant. So good absorbers are good emitters, or good emitters are your good absorbers. Very, 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 very important formula. Okay. So I can write here. According to Kirchhoff law, according to your Kirchhoff law, E lambda at a particular wavelength divided by A lambda is equals to your E wavelength at some constant B divided by A wavelength at a certain constant B. Okay, that means nothing but of your absorptive power beta. Absorptive power of any body will always be equal to your one part of relation, isn't it? That means at a certain constant part of relation. Clear? Is that clear? This is a basic formula you need to remember ratio. The ratio of your emissive power to your absorptive power is a constant. That is E lambda divided by A lambda is also a constant. That means when the temperature is been increased, with increase in the temperature, isn't it? Energy of your emitting is been also increasing, and the ratio of your absorbing is also been increasing, right? Okay. So E lambda divided by, so this one, see these two of them are constant. So I can write here E divided by E of your lambda B, that will be your constant. Okay. So what is the difference between E and E lambda B beta? Can anyone tell me? Or E lambda you can take, sorry. E lambda means at a given part. E lambda B means at a given temperature. When you're increasing the temperature, whatever the ratio of your emittance is there, that will be remaining for me constant, because that will be equal to how much for me beta? A lambda, that will be equal to your A lambda divided by capital A lambda B. Or else you can take small a lambda B also, there is no problem. So let me write this one also capital A, because I'm taking that one there as of your capital A. So this one is your capital A lambda into P. Let's say if there is one body and it is at a temperature of T1. So at a T1 temperature, it is having the emittance as E lambda and absorptance of your A lambda. Now same body at a temperature T2 I'm taking. Now that emittance I'm taking as E lambda B and absorptance I'm taking it as of your A lambda into B. That means if the temperature has been increasing, the power of emitting and absorbing is also increasing. Isn't it? Even if I take your third body right now, T3, then it will be your E lambda B into your dash, and your absorptive power will be your A lambda into your B dash. That means as the temperature has been increasing, the power to emit and the power to absorb is also increasing. That means for a given body, as the temperature has been increasing, the ratio of your E lambda by A lambda is also increasing. That's what it says right now here. So as the temperature increases, the ratio of your emittance and the ratio of your absorptance is also increasing. That was about your Kirchhoff's law. Okay. Next. Wings displacement law. Wings displacement law. Okay. Wing is the name of the scientist beta. So according to this law, I can directly write the relation. Wavelength at a particular wavelength, let me write it. Lambda m into your T is equals to some constant. Okay. That means the product of the wavelength and the temperature, corresponding temperature at maximum intensity of the radiation. Okay. So according to the Wing's law beta, the product of your wavelength into the maximum temperature of the body in the Kelvin is always your constant part of relation, where B is a constant and the value of the B is somewhere around 2.89 into 10 to the power of minus 3 meter Kelvin. This is the basic unit of this one. So you need to remember the graph for this one better. So basic graph, very important one. Here I'm taking the energy of your emittance at a particular wavelength, and here this one is of your wavelength lambda. See, when the scientists were been drawing the graph for this one, they found that this one was the first graph right now. That means as the wavelength was somewhere here right now. That means lambda 1 somewhere here. As the wavelength was being decreased, so the temperature, the emittance power of this one was also being increased. So right now like this. Now this one was at your wavelength of your lambda 2. Then again when the wavelength of this one was being increased, then again it was being found to be your increase, right? Something like this. That means as the wavelength was being decreasing, the ratio of your emittance power was also increasing for the given conditions. Is that clear? Now see, if it is at a temperature of your T1, if it is at a temperature of T2, and here if it is at a temperature of your T3. So I can write here the ratio of the temperatures better. Can anyone tell me? So temperature of your T3 will be greater than of your T2, will be greater than of wave. So whereas the wavelength of your lambda 3 will be lesser than of your wavelength of your lambda 2 will be lesser than of your wavelength of lambda 1. Isn't it? So as the wavelength was being decreasing, the temperature of that one was being found to be increases, and the emittance power of that body was also found to be increases. And E is maximum shifting towards the left. That is, this law is called as of your Wings displacement law. Okay. That means as the temperature of the body has been increasing, the wavelength at which the spectral line intensity is maximum shifting towards the left. Therefore, that play is called as of your Wien's displacement law. You can directly just remember the numerical for your examinations better. Lambda m into your T is equals to some constant, and the B value generally you will be giving in your examination 2.89 into 10 to the power of your minus 3 meter Kelvin. Clear better? Next. Stefan's law. Stefan's law. Okay. See the statement for this one better. The amount of heat radiated, per second from unit surface area, of a black body, that is represented by capital E, is proportional to fourth power of its absolute temperature. That is capital T. This is called as of your fourth power law, Stefan's law, or also we can call it as of your fourth power law. Okay, so the amount of heat radiated per second, from a unit surface area of a black body is proportional to the fourth power of its absolute temperature. See, we don't have much time for the detailed explanation. That is the reason I'm not going for much depth explanation part of lecture. Only the thing which has been required for the competitive track, only that much part only I'm writing here. So this energy is directly proportional to your T to the power of 4. This energy is nothing but a Q divided by your A into your capital T is your temperature. It is directly proportional to T to the power of 4. So I can write here Q divided by your A into your T. Removing the proportionality constant, we get some constant known as sigma into T to the power of your 4. Okay, so that means I can write here Q by your T, amount of heat energy radiated is equals to sigma into your A into your T to the power of your 4, where sigma is known as what beta? Stefan's constant. And the value of that one is 5.67 into 10 to the power of minus 8 watt per meter square Kelvin to the power of your 4. Very important beta. So Q is equals to rate of your energy, and energy divided by time. Q by T is equals to sigma into your A into T to the power of your 4. Or I can say that the amount of your heat energy or amount of your heat radiated per second from your unit surface area, of your black body, capital E, is proportional to your fourth power of its your absolute temperature. That is nothing but of your capital T. Clear? So if the body is not a perfectly black body, then we can write here one formula. If body is not a black body, then I can write here Q by your T is equals to emissivity into your, this one is nothing but of your sigma into your A into T to the power of your 4. Okay, so the value of E lies between 0 and 1. That will be given beta. E is nothing but what beta? Emissivity. You should be giving the emissivity of that one. Clear for everyone? So Q is equals to, I can write here. If I'm writing in terms of a Q, to what is the T here, beta? Can anyone tell me what is the T here right now? This T, whatever I'm writing here right now. So it is nothing but amount of energy radiated per your unit time. Let's say I have written here right now. Q is equals to this one. So E is equals to your amount of energy radiated per unit surface area per unit second. So that is your time, but don't take it as of your temperature. So this is your time. Represented by capital T or small t. Okay, I'll represent it by small t only, otherwise you'll get confused. So better I'll try to write with your capital T. This one is also small t. So this one is your T. This one is also your T. So I can write here Q is equals to your E into sigma A into your T into your capital T to the power of 4. So energy radiated will be equal to this much. If the body is not a black body, if it is not a black body, if it is a perfectly black body, then you take emissivity is equals to your 1 part of relation. Clear, better? Sure. Next very important formula for this one is Stefan's Boltzmann's law. Stefan's Boltzmann's law. Stefan's Boltzmann's law. Important formula. Better. Get a good numericals based on this one. Direct application is more than enough. Okay. So now see, if the black body is at absolute temperature TB beta, so I can take here right now, write the statement. If a black body at absolute temperature, that is nothing but TB, is in an enclosure, at absolute temperature, that is a TS, then the loss of thermal energy, by the body per unit time is called Stefan's Boltzmann's law. That is Q divided by your T. Energy lost per unit time is equals to sigma into your A into your temperature of your absolute body, that is a black body, to the power of 4 minus temperature of your surrounding to the power of your 4. So Q by T is equals to sigma into your A, temperature of your black body minus a temperature of a black body to the power of 4 minus temperature to the power of Ts to the power of your 4. If the body is not a black body, then how do you write this relation, beta? If body is not a black body, then I can write here Q by T. We introduce a term called as emissivity into sigma into your A into temperature of the black body to the power of 4 minus temperature of the surrounding to the power of your 4. This will give me the answer. Okay, I'm writing on basic mathematics, you see beta here. If you can remember, that will be more easy for doing the calculations. For calculations, when you get T to the power of 4, so what you can write is, see this, temperature of the body to the power of 4 minus temperature of the surrounding to the power of your 4 can be written as of your temperature, that is a TB square plus of your TS square into your, this one is your TB square minus of your TS square, same thing, or else that will be equal to your TB square plus of your TS square into A square minus B square formula we are having, better. I'm writing with the other pen, so it will be easy for you to understand. This will be equal to your TB plus of your TS into your TB minus of your TS. Calculations, it will be easy if you can remember this relation right now. Okay, so TB to the power of 4, temperature of the black body to the power of 4 minus temperature of the surrounding to the power of 4 can be written as of your TB square plus TX square into your TB square minus of your T, that is A square plus B square into your A square minus B square. A square minus B square can be written as what, beta? A plus B into your A minus B form. I'm just expanding that one and try to do the calculations, you'll get the answer for that. Clear, beta? Sure. The next one is very important, beta. When the heat lost when the heat lost by radiation is considered. By radiation is considered. Okay. Then how do you write this relation? Radiations, if I am considering, see here, dq by your dt. dq by your dt is equals to what, beta? M into your specific heat into your d theta divided by your dt. How we got from this one? We know the formula q is equals to ms into your delta theta. So if I'm writing dq, so dq is equals to your ms into your d theta. So if I'm dividing by time, so it is d theta divided by your dt is equals to m is a constant, s is a constant. So it is a temperature difference divided by your time. Okay. So what is your m? M is nothing but if your mass of the body. M is your mass of your body. S is your specific heat of your body or material. Specific heat of your material of body. Material of your body. So using Stefan's law, now I can write using your Stefan's Boltzmann's law. So dq by dt already we got better. We know that emissivity, that is emission, is directly proportional to your right now. So I can write here right now dq by dt. See this formula in the back side. So dq by dt is equals to E into sigma into A TB to the power of 4. That will be equal to your ms into your d theta by dt. So I'm writing that one here right now. You see, I'll rub this part. So dq by dt will be equal to, just a minute. Yeah. See here, dq by dt. dq by dt means m into s into your d theta by your dt will be equal to your E into sigma into your E into sigma into A into your temperature of the black body to the power of 4 minus temperature of the surrounding to the power of your 4. Okay, that means d theta by dt I can write as d theta divided by your dt is equals to E into sigma into your A divided by mass of the body, specific heat of that material, into your temperature to the power of black body to the power of 4 minus temperature of the surrounding to the power of your 4. Very important relation. What is d theta here? But temperature difference per your unit time. Done. So this d theta by dt is known as what, beta? Rate of your cooling. The rate of your cooling, actual formula. So d theta by dt is equals to E sigma A divided by ms into your. If mass is not given, better, you can even take mass is equals to volume into density. Volume is equals to 4 by 3 pi r cube into your density. You can take even like that. Area of the body, if I'm given for the spherical bodies, 4 pi into your r square for your spherical bodies. Depending upon the radiations, you can write the given conditions. Clear, better? So for the spherical bodies, I can write here for spherical bodies. If mass is not given, mass is equals to volume into density. Volume is 4 by 3 pi into your r cube into rho. That means mass will be directly proportional to your radius of the cap. And area will be directly proportional to the square of the radius of that. Okay, so you can use that relations and try to simplify the problems part of relation. Okay. And some important points in this one say right now. D theta by your dt is inversely proportional to mass. Okay. So tell me in the solid sphere and hollow sphere, which will lose the rate of loss will be more for which one, beta? A solid and hollow spheres of same material of equal radius, they are heated to the same temperature, beta, and allowed to cool the same environment. Then hollow sphere will cool faster. Okay. Of solid and hollow spheres. Okay. Hollow sphere cools faster. Okay. But rate of loss is same for both of them. Rate of loss is same for both solid sphere and hollow sphere. Okay, very important point. But d theta by your dt is inversely proportional to mass of the solid and hollow sphere. Hollow sphere will cool faster, but rate of loss is same for both the solid and as well as of your hollow sphere part definition. Okay, and the last part of this one is your Newton's laws of cooling. Newton's laws of cooling. Okay. See here. So the rate of loss of heat of your body is directly proportional to what, beta? Difference in the temperature of the body and the surrounding part. That is dq by your dt is directly proportional to your T minus of your T naught. T is your temperature of body, and T naught is a temperature of surrounding, or I can say hot body right now, isn't it? So if I'm removing this proportionality constant, dq by your dt is equals to some constant minus of your b into your T minus of T naught. Why minus? Because it is losing. B is a proportionality constant and it depends on beta. B depends on your nature of your material, comma, shape and area of your cooling. Okay. Now, as d cube by your dt is equals to m into s into your d theta by your dt. So I can write here right now dq by dt will be equal to how much, beta? So therefore I can write here dq by your dt will be equal to your m into s into your d theta divided by dt will be equal to minus of b into T minus of your T naught. Okay, that means d theta divided by dt is equals to your minus of your b into T minus of your T naught divided by your mass into your specific heat. So rate of your cooling is inversely proportional to your mass and as well as of your specific heat. So this total one I can take constant beta. So if I'm writing in terms of a basic formula, theta 1 minus of theta 2 divided by your time t is equals to some constant k into your, this one is your theta 1 plus of your theta 2 divided by 2 minus of your theta naught, where k is equals to some constant, that is b by your m into your s. Okay, so theta 1, theta 2 are your temperatures, and here T is nothing but of your temperature of the initial body and final body, and theta naught is the temperature of the surrounding. Very important formula. Okay, is it clear? Very important formula for the Newton's laws of your cooling. Let me take one small graph of this one. See, rate of your cooling is equals to some constant k into, this one is of your temperature of your body, T minus of your T naught. So T is nothing but what, beta? Theta 1 plus theta 2 divided by 2, and theta naught is nothing but theta naught. Okay, and d theta is nothing but here right now initial temperature minus final temperature, and time is time. So anything divided by time is known as rate, beta. Rate is equals to k into this one. So that means R is equals to k into T minus of your k into your T naught. So compare it with your straight line equation, beta. Compare it with y is equals to m into your x minus of your c. Okay, so what is happening right now, beta? What is the slope for this one? Can anyone tell me? So slope is right now represented by m. That is nothing but equal to your tan theta, and that will be equal to your how much, beta? That will be equal to your how much? Slope is represented by what, beta? M. That is nothing but of your k, and that k will be equal to how much for me, beta? B divided by m into your s. Clear? So I can say that tan theta is inversely proportional to the mass and also the specific heat. Very important relation. Okay, that means if I'm drawing the graph for your rate versus your rate on y-axis, on an x-axis we are taking right now for me what, beta? This temperature, that is nothing but of your T. Okay, so what will be getting right now? So we'll be getting a straight line like this. So y is equal to m into your x. This is your T, isn't it? So it is y. This is your m into x minus of here. This is totally a constant. So we'll be getting a negative constant, so that will be in the downward direction. So it is making an angle of your theta. Done, beta? So these are all the formulas you need to go through it better. So start doing the working of this one in the next session of your class. First one in the convection, this is the formula we need to remember. dq by dt is equals to your directly proportional to area and indirectly proportional to temperature difference. Removing the proportionality constant, we get some constant known as h. H is known as of your conventional constant. Next one is about your radiation, some theory related to this one. In this one, the formula which you need to remember is intensity is inversely proportional to the square of the distance. Then next one is about your emissive power. So emissive power is nothing but of your what? The amount of your energy radiated. The amount of your energy radiated per unit surface area per unit second at a given temperature of a given wavelength range is called as of your emissive power. So E is equals to Q by E into T. Unit is watt per meter square and it depends upon your nature of your surface and also your temperature. Next one is absorptive power, the ratio of your energy absorbing divided by your energy emittance or energy emittance particulation. Whatever it is absorbing, if it is giving the same, then absorptive power will be equal to 1. So it depends upon the nature of the surface and the temperature of the body. And for the perfect black body, A value will be equal to 1. What do you mean by emissivity? Emissivity is the ratio of emissive power of a body divided by emissive power of your perfectly black bodies. The next one is of your Kirchhoff laws. This formula you need to remember. This graph is also very important. And Stefan's law formula, Q is equals to E into sigma A T to the power of your 4. Boltzmann's formula, Q by T is equals to sigma into A, temperature of the body to the power of 4 minus temperature of the surrounding to the power of 4. So this formula you can remember for doing the numericals. The next one is sum of the relations. If mass is given in the form of sphere, mass is equals to volume into density. Volume is 4 by 3 pi r cube into rho and area is equals to 4 pi into your r square. Okay. And the last one is dq by dt is inversely proportional to mass. So rate of loss is same for both the solid and hollow sphere, but of the solid and hollow sphere, which cools the faster means hollow sphere will be cooling the faster part. And the Newton's laws of your cooling, dq by dt is equals to some constant minus b by m into your s, t minus of your t naught. B is a constant, mass is a mass of the spherical body, s is your specific heat of the given conditions. So if I'm taking the graph of your rate better, because temperature divided by time is known as a rate, so that I'm taking it as of your r, this k, this is the total t minus of t naught. Comparing it with y is equals to m into x, we are getting a straight line graph also having the negative intercept. And this tan theta is inversely proportional to the mass and inversely proportional to the specific heat. So these are the formulas which you need to remember in your heat transfers for your examinations. Clear, better? Then we'll try to start doing the numericals in the tomorrow session of your class. I'm already having an assignment, so I'll send you them. You'll try to do them, and remaining some good applications, 10 or 20 problems, we'll try to do on the heat transfer in the tomorrow session of a class. Okay, beta? Sure. Take care, beta. Bye.